Good afternoon, everyone. On behalf of the organizers, I would like to welcome you to today's CERN Colloquium. We are very happy today to have a very distinguished speaker, Cumrun Vafa. Cumrun is a Hollis Professor of Mathematics and Natural Philosophy at Harvard University. I guess he's also a chair at the moment. He was born in Iran and then received his higher education in the US. His PhD is from Princeton, and then I guess he became faculty at Harvard. Cumrun is known for his numerous foundational contributions to string theory. He was one of the founders of the duality revolutions. He had seminal works on the theory of quantum black holes. And in the last years, and this is very exciting for CERN, he was putting forward this program, which he will tell us today, which brings string theory closer to phenomenology and cosmology. And today he will tell us about the state of the art, which we are very excited about. Cumrun, thank you very much.
Thank you. Thank you very much for the invitation and the kind introduction. It's a great pleasure to be here. I guess in some sense the center of connecting the high energy physics to the real world right here. So the talk I'm going to give is connections between the kinds of things that I have been involved with a large number of colleagues, connecting quantum gravity to real world predictions, and that's the thing I want to talk about. Maybe I don't know if the light can go down here from the front. Maybe it's a bit, that'll be good, but anyhow. So it's based on many papers in string theory literature, but more specifically, the kind of things that I'm going to emphasize for this talk is based on the collaboration with these collection of people. You can read the names, including Irene here and a number of other colleagues who have been instrumental in these ideas. So it's a collaborative effort by a number of people. So string theory is believed to be a fundamental theory of nature leading to a consistent theory of gravity, but it has the reputation, perhaps justifiably, of not being able to make any concrete predictions about observable physics other than gravity exists or some qualitative features. In this talk, I would like to present some concrete predictions from string theory and explain how we make this, why we come up with these predictions, what are the assumptions leading to these predictions, and the fact that these predictions are actually testable not just in the far future, but actually in the near future. In fact, some relevant experiments are actually ongoing right now. So to set the stage, I want to remind you of some of the puzzles that appear in physics. The hierarchy of scale puzzles. This is some version of what Dirac would call the strange feature, that there are these large numbers in physics appearing. So I'm updated his version of this puzzle to the observations today. So the supreme among them is the fact that the dark energy is roughly 10 to the minus 120 in the fundamental units in physics. Huge number. Hugely small number, that is. The age of the universe now, if you invert it, or if you want to say it's 10 to the 60, or inverted 10 to the minus 60 in the fundamental units, in Planck units, which is, if you want to compare it to the energy scale, it's 10 to the minus 40 GeV. The mass of the neutrino is the next scale we encounter, which is 10 to the minus 30 in the fundamental unit, Planck units, which is about 10 to the minus 10 GeV. So this column here is the column written, the mass units in the fundamental Planck units. And here I'm trying to convert them to GeV units so you can see the same scale in the GeV scales. And I'm not being precise with factors. There's factors of a 10 or 100 here and there, so I'm just rounding it up or down. The QCD scale, which is basically close to the weak scale up to some factor of 100, is about 10 to the minus 20 or so in the fundamental units. And there's even believed to be, based on the observations of measurements about the Higgs here at CERN, that the Higgs potential may have an instability at the energy scales of around 10 to the minus 10 or 10 to the 10, 10 to the 11 GeV, that range is expected to have some kind of instability. And of course, there is a Planck scale, which I didn't even write down here, which is 10 to the 19 GeV, 10 to the 18 or 19 GeV. What is striking about these scales is this regular features of powers, roughly powers of 10 to the 10 going between these scales. Now, of course, there could be some intermediate things happening in between these scales. We don't know. But at least these are, given the scales we have today, these are somehow strikingly separated, but in very regular fashion nevertheless. And it was this regularity or some of these big numbers, but somehow felt regular to Dirac, which suggests that maybe there's an explanation in terms of powers rather than in terms of numbers, multiplicative factors, that could explain such features. Any such things, naturally, you would go after the most extreme thing here, which is lambda itself, the dark energy. So somehow the question is there any relation between all these scales, and in particular, does there have any relation to do with the dark energy itself? Now, the very notion of particle physics has been based on the idea, in many ways, that we don't need to know everything at the highest energies to make some understanding of physics, let's say of accelerators and so on. And the idea is that the scales decouple. Whatever happens at the very, very short distance, at a very high energy, is not going to impact what I'm doing in the experiments today, and therefore I don't need to know too much about those details. I can focus on my energy scale and write down the effective field theory at that scale and describe the physics there. That has been very powerful in making a lot of predictions that have been confirmed. But among the failures of these approach has been the issues of hierarchies that has been striking and has not found a natural solution. The most basic one is the electroweak hierarchy. Where is that coming from? What is the explanation for that? And these are other kinds of questions that you can ask that could be ascribed to accidents or maybe anthropics or this and that. And somehow there's an uncomfortable feeling that the usual paradigms of the effective field theory approach is not adequate to address these fine-tuning or apparent large discrepancies between these scales. Also, questions that also loom is, what is the nature of dark matter? On top of all this, there's dark matter. What is that? And is it related in any way to dark energy? Seems completely unrelated. At least naively, one talks about energy, one talks about matter. Another question is the smallness of the dark energy is striking, and that's one of the features of dark energy. And an interesting feature is the weakness of interactions of dark matter. These are two features that we know. Are there any relation between these features and these facts together, or they're completely unrelated? So quantum gravity for sure seems unrelated to these questions. That is the usual picture that we have in the context of particle physics, that quantum gravity is something you can ignore when we describe some of these. Maybe not dark energy, but the rest of it seems to be quite independent. Nevertheless, I will argue in this talk that quantum gravity sheds light on all these questions, that we cannot ignore quantum gravity if we have any hope of explaining these features. Now, before I go on, I want to explain why this is not a strange feature. Underlying a lot of ideas in particle physics is, as I mentioned, this decoupling between high energy and what we call ultraviolet and low energy, long distance. Gravity gets strong when you get to the very short distances, Planck length scale or high energy scale of Planck energy, and therefore you would think at energy scales that we are probing it's going to be irrelevant, and that's the underlying feature of it. However, we know that in the context of gravity, ultraviolet physics and infrared physics, the short and the large distance physics, are intricately related, and they cannot be decoupled, that connection. And the very basic feature, there are two examples I can give, and I will give you both examples, and both are related to black holes. So we know there are black holes. That's one of the features of Einstein's equation. When you solve it in the infrared, in the long-distance physics, you can get these solutions that we trust. In fact, we have been observed now. So we have black holes in Einstein's theory. So that sounds like an infrared, long-distance, macroscopic physics solving large-distance wavelengths or deformations of long wavelength context of Einstein's equation. On the other hand, the following question arises. Suppose you take two particles, like electrons, and smash them together at energies, huge energies much, much higher than the center of mass energy being Planck energy. At huge energies, you bring them together, what's going to happen? Well, if you bring them close together with a high enough energy, then they are inside the horizon of a would-be black hole total energy, and therefore they should form a black hole. And so therefore, the very high energy version of it converts this question to a question about black holes, and if there's large enough energy, you are talking about a big black hole, which is now described by infrared physics, in which case we know there's Hawking radiation and all that happens. So we have already a prediction of what happens at the extreme high energy of this collision. So the extreme high energy collision has a qualitative picture prediction based on large distance description of Einstein's theory. So this ultraviolet, namely high energy scattering, and long distance physics, which is solving these equations, are connected through the magic of black holes. Black holes connect a lot of these features of ultraviolet and infrared in an unavoidable fashion in the context of quantum gravity. That is one version of the puzzle I just told you. Another way of saying is Hawking's entropy, or Bekenstein-Hawking's entropy for black holes. What is a black hole? Well, if you look at the energy spectrum, and if you go to higher and higher energies and ask what are the degeneracy of states in your theory, we know the low energy states that we have, and if you go higher and higher, we don't know exactly what happens, but if you go really, really high, by the time you get to energy scales much, much bigger than Planck, we do know that in that context you form black holes, so therefore they are black holes, but Hawking tells you that the entropy of black hole is given by the exponential of the area of the black hole divided by 4 in Planck units, and so there's a prediction of the density of states for very, very high energies. Again, this macroscopic black hole is making a predictions for extreme high energy density of states, which is bizarre from the viewpoint of effective field theories. A macroscopic object is predicting the high energy behavior of the theory. So the question is, how does this connection work? What is this feature that couples the ultraviolet short distance to this long distance? And the Swampland program basically summarizes the lessons about quantum gravity we have learned from string theory. So string theory, we believe, gives you a consistent quantum theory of gravity. And in that context, we can actually ask what are the possible things that we learn about infrared physics from a fundamental ultraviolet complete theory like string theory. What are we learning? What are the features? Well, there are many solutions. Do the solutions have a common feature? Do they have something that all of them satisfy? Is there some features that we can say is the inescapable property of consistent quantum gravity theories? Now, we have to be careful, because a skeptic would say, how do you know that string theory is the only theory of quantum gravity? And that's a fair criticism. So we should somehow not necessarily assume string theory is the only game in town. And the question is, nevertheless, we believe that string theory are giving you at least consistent subset of possibilities. Within that subset, do we have a common feature? Now, if we find common features from that for string theory, we could still be under the lamppost effect that, we are only studying the things that we know how to do, so therefore we might miss the actual story. So we then have to step back. Once we see commonalities and patterns, we should ask, can we explain those patterns without using string theory? Could we appeal to some more basic principle, like unitarity, the properties of black holes that we know regardless of string theory, and so forth? Can we use some extra features that we can actually understand those facts? In other words, we use string theory as a hint of a principle, and nevertheless try to seek that principle without using string theory itself and see if we can justify it. That's the way we hope to do. In other words, we do not want to think that we are assuming string theory is the only consistent theory of gravity, but use that to get features of what all quantum gravities should satisfy. I should add that doing this exercise is convincing us more and more that string theory is the only consistent game in town. But that's not goes into the assumption. So in other words, we are open to the possibility that there are other things, but string theory, nevertheless, the restrictions we are getting seems to be explainable by something beyond string theory itself, which seems to reinforce that fact. So what are these lessons? Well, what we have learned from string theory is that quantum gravity theories are far more restrictive than we had imagined. In fact, very few effective field theories emerge in the infrared limit of ultraviolet complete quantum gravity theories. That is a good news, because when you have restrictions, you can make predictions. Restrictions are great for making physical predictions. Not everything goes. In fact, effectively, if you take a random theory of particles that you say, can this be coupled to quantum gravity? Or another way of saying, can this emerge in the infrared limit of some quantum gravity theory? If you choose a random one, the answer will be no. In other words, the generic quantum field theory cannot be coupled to gravity. That's the lesson. It's only a rare subset of them, measure zero almost. Well, measure zero. It's very rare that you can get the right theory out. So quantum gravity is not like the usual paradigm. You take your field theory and couple to gravity. That mechanism classically makes sense, but quantum mechanically fails. So this idea that effective field theory kind of says, oh, there should be no problem. You just take this and just couple to gravity. Who cares? We should have a way of doing it. Seems not to work. And that is a big paradigm shift. And that's the main lesson I want to convey today. So that we get a lot of restrictions. Now, we could get these restrictions, and we can also combine them with observations. So these are restrictions. It doesn't predict what will happen. It will say, well, this can be less than or equal to that can be bigger than or equal to that, and so forth. It gives you some boundaries of possibilities. But then you say, oh, I have observed X fact, or Y fact, or Z fact, and I know that it's restricted to be like this. And then these two principles combined with observation, can lead to new predictions. And that's the way I'm going to be using it. So the way we think about it is that in string theory, we have these extra dimensions where we have to compactify properly with some interesting spaces, which are solutions to string equations. And what we get, that's in the ultraviolet description of the theory. And by the time we get to infrared, which gives you some specific possibilities, they are far rare things appearing in the landscape of naive possibilities. So the possibilities of what we could be getting, we call this green space, we call them swampland because they are not allowed. And the ones that we do get, which is the good landscape, we call the consistent quantum gravity landscape. And presumably, one of them is where we live. That's the universe which is consistently coupled to quantum gravity. The standard model and so forth are there. So what are some of these restrictions? I'll just give you one example. Gravity is the weakest force in any quantum theory of gravity. This did not have to be the case. If you take a quantum field theory, you can make gravity be stronger naively by choosing the parameters. If you have an U1 gauge theory, you can put an electron and make the mass of the electron to be bigger and bigger and bigger and bigger so that it's stronger gravitational force between pairs of electrons than electric force. So there is no a priori reason this has to be the case. But it turns out that in all these theories of quantum gravity that we are getting from string theory, gravity is always the weakest force, just like our universe. Ideas related to black holes seem to support this. So again, you can connect this observation with properties of black hole and their evaporation. In fact, you can do even better. So, for example, in the context of U1 electric force, you can show that the basic entity of basic particles, let's say electron, which carries that electric charge, has a mass which is, roughly speaking, up to some coupling constant factor, less than m Planck, and up to some coupling factor less than lambda to the 1/4, where lambda is the dark energy, which is roughly the neutrino mass scale. So the fact that the mass of the electron is bounded between the neutrino mass scale and the Planck scale would follow from such restrictions. So these kind of pictures, they are not very predictive, namely it's a huge range between the neutrino scale and Planck scale. But nevertheless, there is some kind of a boundary here. You cannot do anything you want there. For any quantum gravity, we believe the rank of the gauge groups you get in the infrared are finite. So suppose I take a theory in 4 dimensions, and I say, well, what's the rank of the gauge group? You say, well, I don't know. Choose a random one. SU1, SU2, SU3, SU4, SU10,000, SU10 billion, arbitrary one. Pick one. Well, if you choose a random one, between 1 to infinity, the generic number is going to be infinite or something. It's going to be huge, whatever. But we say, no, that's not the case. There's a bound on how big it can be, which is strange. Now, this is not because the quantum field theory itself is bad or anything. They are great field theories. For example, if you take the maximally supersymmetric theories in 4 dimensions, which allow matter, this is the n equal to 4 supersymmetric Yang-Mills theory, you would think this theory should be great because it has supersymmetry, but more than that, it's actually a finite theory of quantum field theory. There's no ultraviolet divergences in field theory. It's beautiful. Conformal theory, nice. Everything is nice about these theories. But you want to couple them to gravity, it fails if the rank of the gauge group is bigger than 23. So if you have SUN, all the n's bigger than 24 are in the swampland. Not because the field theory is bad, it's a beautiful field theory, finite. But gravity does not fit that way. Gravity does not fit with the dynamical gravity. By that I mean you cannot have a 4-dimensional gravity coupled to them. Of course, they can couple to a higher dimensional gravity, like you can have a 4-dimensional field theory coupled to a 10-dimensional graviton. That could happen, but not in 4D, not the dynamical gravity in 4D. Another thing that we are going to be, one of the main stars of this talk is going to be the distance conjecture or duality conjecture. And this is another one of those features that we have learned from string theory. So what does that mean? What does distance mean? So in physical theories, we have parameters like coupling constants, the expectation of fields and so forth, that you can in principle vary. In the quantum theory of gravity, in fact, there are no parameters. It turns out all the parameters in the theory are dynamical. That means they should be viewed as expectation values of some fields. You can change them. In other words, if you have a coupling constant, which is 0.5 here, there should be a physical process which makes the coupling constant in this region become 0.6 or 0.3 or 0.2. It's dynamical. You can change it. So there is nothing which is just fixed. It's just nothing is fixed. It could be fixed in a particular vacuum, but you can vary. It's dynamical. So what happens if you change these parameters? So this parameter space is what I'm drawing here. This is the parameter space, let's say, some high-dimensional space of all the parameters in your theory. And you move away from one value to another value. What we learned, and this is really perhaps the most important lesson we have learned in string theory, is that when you go to far away values for these parameters, be it extremely small or extremely large, what you find is that your effective field theory breaks down. Always. Always breaks down if you go sufficiently far away. And the way that happens is that you get a tower of light particles becoming lighter and lighter, and these original states were massive that you had ignored in your effective low energy physics, but they become more and more lighter and lighter and become smaller than your cutoff if you go farther and farther away in the parameter space. So if you in the parameter space, you go, for example, you make your coupling extremely small or extremely large, you get this huge tower, not just one particle, infinite number of particles becoming light. So there's no way to put them in your effective theory because there are infinitely many of them. You have to completely reformulate your theory, and that is duality. You go to a dual description of that theory. That's duality. So duality is precisely this feature that at infinite distance or large distance in parameter space, you get this tower of particles coming down. So if you view this phi as a parameter space, you get these towers of particles exponentially going down in the distance in this parameter space. Moreover, you can ask, what is the nature of this tower of light particles? It turns out, and this is some work which was done here, which was conjectured here by Wolfgang and collaborators, that this tower can have only two possible ways that it can be. One of them is that some dimensions open up, and this tower is nothing but long wavelength excitations, let's say of graviton or other fields in this theory. So that gives you a light tower of what we call Kaluza-Klein particles. Or it could be a tower of strings which become tensionless in this limit. That is, you have a tower of excitations of a light string, fundamental string. Both of these towers, moreover, are weakly interacting tower. That's part of the features of this large distance physics. You not only get an infinite tower, but of weakly interacting particles with each other. So we are automatically expecting whenever you go to infinite distance or large distance in parameter space, you should look for a tower which is weakly interacting. Always. That's one of the lessons we have learned in string theory. More than that, we have actually known how fast it goes down. In other words, if I have a parameter phi and it goes a distance, large distance in phi, the mass goes with an exponential form down, where this parameter, if you're in d-dimensional space-time, in Planck, if I write phi in Planck units, it's bounded below by 1 over square root of d minus 2, where d is the space-time dimension. And if you have some dimensions opening up, the maximum it can be is if capital D dimensions open up, total dimensions you have is capital D, you get it bounded by this on the right. So this is one of the features that has been seen in string theory. This feature has not been proven without using string theory. So this feature of duality is one of those things we have yet to prove for every theory of quantum gravity is true. We believe it's true, but we have not gotten to the stage where we can derive it from black hole physics, even though we think something along these lines should be derivable. But it's true in all string theory examples. So this is true regardless of which example you choose in string theory. So I'm going to assume that this is true, that masses go like this if you go far away in field space. And moreover, that it can be either a tower of excitations in a bigger space opening up or light string states. Now, this tower can also have an application in the context of when you have a cosmological constant in the de Sitter space or anti-de Sitter space, depending on the sign of the energy, if the sign of positive or negative. And in that context, the distance relation goes like lambda to some power, where lambda is the dark energy, if you take the absolute value of it to some power, where this power is again order 1. A lot of evidence for this exists in the case of ADS. In fact, the holography, one of the celebrated features of quantum gravity that we have discovered in string theory, has this feature, where lambda is negative, and all the solutions happens that if you have a tower of states, if you have a collection of sequence of anti-de Sitter spaces with negative cosmological constant, and if this approaches 0, as lambda goes towards 0, you get a tower of particles which goes like lambda to that power. So you get a tower of particles coming down. And the way that happens typically in the context of holography is that as the ADS becomes flatter and flatter, what happens is that an extra space gets bigger and bigger. You cannot have a situation where ADS becomes flatter without something becoming bigger. You always get an extra stuff. So that's the nature of all the examples we know in the context of holography. In the context of de Sitter, one can argue that the exponent is less than or equal to a half and bigger than or equal to 1 over the dimension of space-time. One side of it is easy to argue, basically based on unitarity arguments, what's called the Higuchi bound. The other side is a kind of a genericity statement, that is, any cosmological constant gets a contribution of the form of m to the d, and therefore the smallest it can be, at least it will have at least a 1 over d effect there. Now, what do I want to do before I do this? So what do I want to do? I want to apply this to the most extreme parameter in the real world, the cosmological constant itself. It's 10 to the minus 122 or so. That's a tiny parameter. So this principle should apply to it. So without doing anything, you would immediately deduce, oh, in our universe, right now, there must be a tower of light particles, which are weakly interacting. What is that tower? Why haven't we heard about this tower? They are weakly interacting tower? Where is it? Why haven't we talked about it? What is the nature of this tower? So this immediately drives us to ask this question in our universe. So, in principle, whatever that m is, the mass that appears here, the gravity should get modified at that scale. Why is that? Well, because the tower that I'm talking about will have higher spin fields in it, and in particular spin 2 field in it, and it does modify gravity force. So that means that one way to probe this is that whatever mass scale you have, you should get a modification of Newtonian gravity in some form or another. Whether it's extra dimension opening up, whether there's a light tower of strings, at this mass scale, something should change. So this mass scale, this tower of particles that are appearing, would have physical consequences that gravity should be able to see. Now I want to apply this to the dark energy in our universe. But in the context of our universe, we know gravity, Newton's gravity is valid up to about 30 microns at least. So the 1 over r squared force law works up to at least 30 microns. This is the experiments by Adelberger and collaborators. And if you do this, and if you put lambda to the powers, if you put lambda to the powers of different powers, you find that all of these other ones will give you a far too small a mass. And barely the 1/4 one would work. If d is 4, if you put it down there, you get m to the lambda to the 1/4, which is barely okay with this lambda. It's basically on the same range that has been probed now. That means that we are exactly at the boundary of violating this, and therefore there must be something happening right around the next round of experiments, in that if you take the mass scale associated to about 30, the mass scale associated to the cosmological constant to the power of 1/4, you get something in the orders of tens of microns or around that range, which is precisely around the range of 30 microns we have. Of course, we cannot predict the order 1 numbers in front, but this gives you a scale. So precisely the scale is around the same scale as has been probed up to now. So this is already telling you, wait, therefore we are expecting the tower of scales to be related to the distance scale or to the mass scale, which is the inverse of this length, which is lambda to the 1/4, which is very close to the neutrino mass scale. So if you put that in, and you find that basically you're predicting that there's a tower, maybe in the 0.01 to the 0.1 region, electron volt, maybe slightly more than the neutrinos masses, which goes like lambda to the power of 1/4, and let me write this as lambda to the 3/12, as you will see why I'm doing this later. This gives you a length scale. This is a predicted length scale of the order of 1 to 10 microns. So we are expecting that something has a mass scale in this range, and the Newton's experiment in the scale of 1 to 10 microns should start showing deviations from 1 over r squared force law. Now we can ask, Is it a tower of excitations of graviton in extra dimensions, long wavelength, like Kaluza-Klein excitations, or is it a tower of light strings? It cannot be a string because the strings get strong at the same scale as this mass, and therefore that means we would have been producing black holes at the electron volt scales when you have the colliders of any energy bigger than electron volts, which is not the case. So it cannot be a tower of light strings. So the only possibility is the Kaluza-Klein tower, the tower of large dimensions. Some large dimensions should open up. How many dimensions should open up? How big are they? Well, we know that how big they should be. They should be of the scale of the micron. How many dimensions are there? 1, 2, 3, how many of them? Well, for that one, you can actually relate the higher dimensional Planck scale, because in the higher dimensional theory, when some dimensions are opening up, there's a higher dimensional Planck scale. You can relate that higher dimensional Planck scale to the mass scale of the tower we are talking about in Planck units, with some power of m Planck. I'm not writing here because I'm doing everything in m Planck equals to 1 units in the fundamental units in physics. So if you do that, you find that all the other cases other than n equals to 1 is ruled out. So the only possibility if you have n extra dimensions is that you have exactly 1 extra dimension of this order of the micron scale. 2 extra dimensions are borderline. It gives you a TeV scale, but they can be ruled out in yet another way. So basically, the only possibility is 1 extra dimension. This is very different from the large extra dimension scenarios people were suggesting it 20 years ago or so, where the motivation was to make the Planck scale be the weak scale, and the number of dimensions should have to be at least 2. Here, it's the dark energy which is driving the show, and its only possibility is 1 extra dimension, no higher, not 2 or higher. So it's a very different motivation and parameters that we are getting. And this gives you a prediction for the higher dimensional Planck scale, which is mass to the power of 1/3. If you just put n equals to 1 here, 1 extra dimensions, you find lambda to the 1/12, and you find that's about 10 to the 10 GeV. Lambda to the 1/12 is appearing, so I just want you to take a note of this. So roughly speaking, to see these numbers, just remember lambda is 10 to the minus 120 roughly. So 1/12 power of this 10 to the minus 10 in Planck units. So this is roughly 10 to the 9 GeV, 10 to the 10 GeV range. So we already get a scale which is not the Planck scale in the 4D, but lower by a considerable amount, but not too much lower, not to the weak scale, but 10 to the 10 GeV. So the dark dimension is the proposal motivated from this distance conjecture in the swampland program, which is there's 1 extra mesoscopic dimension in the length scale 1 to 10 microns. And the fundamental Planck scale in that extra dimension in the 5-dimensional theory is lambda to the 1/12, which is about 10 to the 10 GeV. So now I come to phenomenological aspects of this theory. If you have 1 extra dimension, which is this big, relatively speaking, a micron, if you can ask, do the things that we are made of, electrons and all that, do they live in this 5-dimensional space-time? And the answer is no. And the reason for that is, if they lived in this 5-dimensional space-time, they would have had excitations of various momenta. Let's say the no excited version is our electron, then there would be 1 wave number, 2 wave number, and so on, separated by scales of 1 over length scale of this extra dimension, which is milli-electron volt to electron volt, which is very tiny. So you have a tower of electrons, towers of quarks, towers. That's not our universe. So the only way this can be compatible with observations is that we are localized in the extra spatial dimension that we are getting. So we should be localized in some brain, some defects, a 3 plus 1 dimensional defect sitting in this extra dimension. So that's the only possibility. So again, I want to say that we are now using combination of ideas from swampland and observations. I mean, we could not have deduced these without partly going back and forth between one or the other. So this is a combination of what observations tell us, that there is no tower of electrons, just one electron, and then we can pinpoint what are the options. There are three potential applications to particle physics just from this point, just without any further thinking. The first one is, could this be instability in the Higgs potential, which is around 10 to the 11 GeV expected, could that be related to the fact that the fundamental scale in this fifth-dimensional theory is 10 to 10 GeV? If you go to that scale, the quantum gravitational effects are going to be important in the theory, and therefore it's going to dramatically change everything. So that's the natural question, and that's the one possible application. So the 10 to the 10 GeV becomes a natural scale in physics, which is otherwise ad hoc. So we already know from the observation that something is going to happen around that scale, but grand unified theories are giving you a different scale, and Planck scale is different, and unless there are extra particles in the middle that we haven't seen and so forth, this would be sounding like a strange possibilities. But at least in this context, we don't have to look for anything further. Gravity could potentially itself do the job. Another application is potentially to neutrino physics. Now, this idea that how does the neutrino get its mass has been one of those things that have theorists have worked in quite different ways over the decades. One of them, in the context of large extra dimensions, people try to do the following beautiful idea. Could it be that the left-handed neutrinos, which is now stuck to the 3 plus 1 dimensional part of this space-time as a defect, could it be paired up with the right-handed neutrinos which are living in the bulk? In other words, could it be the right-handed neutrino being 4 plus 1 dimensional object, coupled to the left-handed part, which is 3 plus 1 dimensional ones? Could you pair them in this way and give mass to the neutrinos? And this idea was done. And if you just use the parameters of this theory, if you just take the neutrino, right-handed neutrino in the bulk, coupled to the left-handed one, which is in the boundary, you write down the naive mass matrix, you get, without doing any work, you get the right scale for the neutrino mass without doing any further things. So this already says that this idea that the dark energy comes out connects the neutrino mass scale to the lambda to the 1/4 if you assume the Higgs scale is lambda to 1/6 roughly. So that sounds like a very attractive possibility, that the neutrinos could be that. If that's the case, then you will get not only the neutrinos, the 3 neutrinos that are becoming active neutrinos, you get an infinite tower of sterile neutrinos coming from the bulk, whose mass scale is similar to the neutrino mass scale, but there are a tower of them. That's the separation of their mass. So this naturally suggests that you should be looking for sterile neutrinos in experiments. In fact, you can turn this around. You could say here, let me go back, in this formula here, I use the expectation value of the Higgs field to get a prediction for the mass of the neutrino, but that I put from the observations what it is. Could I have derived what the Higgs field wave is? Could I have derived the electroweak hierarchy too? That's the question. It turns out that if I just assumed, and I don't know how to justify this, but if I had assumed that the sterile neutrino mass scale is the same as the active one, it fixes the Higgs wave to be this. In other words, the lack of hierarchy in the neutrino sector, meaning active and sterile neutrinos have roughly the same mass scale, is equivalent to saying the Higgs field has a wave which is around the observed value. So the lack of hierarchy explains the electroweak hierarchy. If we have a way to explain why there should not be a hierarchy in the neutrino sector, we have explained the electroweak hierarchy. And in this case, it's interesting to note that the mass of the neutrino is the same scale as the mass of the tower, is the same scale as the mass of the sterile neutrino, and all of them are, this should be lambda to 1/6 here, not 1/12. These are all lambda to the 1/4, and this is lambda to the 1/6. Third potential application to particle physics is axion physics. The axion decay constant must satisfy. So if you take an axion is living naturally on the brain, because on the defect we live in, because that couples to the QCD. I'm now talking about QCD axion. If you're talking about QCD axion, since QCD lives on this brain, it's natural to assume that the axion itself lives on this brain. And if you do that, you find, since the value of the decay constant of axion cannot be higher than the Planck scale, you predict that the f of axion is less than about 10 to the 10 GeV. On the other hand, experimental bound tells you that the decay constant of axion is bigger than about 10 to the 8, 10 to the 9 GeV. You're basically stuck. So from the bound that you're getting and the experiment combined, you're predicting that the axion decay constant is close to 10 to the 10 GeV, which itself is the higher dimensional Planck scale, which is lambda to the 1/12th. And if you compute the mass of the axion in that limit, which is the QCD squared scale divided by f of axion, you find this lambda to the 3/12, which is again the same scale as the mass of the tower, the mass of the neutrino, and the mass of the sterile neutrino, as well as the mass of the axion, all the same scale, near each other. And all given by a power of lambda, namely lambda to the 1/4, or 3/12. In fact, this range of axion mass is exactly in the range of which the kind of experiments that were being done in CERN for the axion search. And now the continuation of that is I think, a joint project between CERN and DESI, if I'm understanding correctly, called International Axion Observatory, which expects to have a baby version of this search happening in the next 5 to 10 years, which searches exactly this range of axion parameter space. And so this is very interesting and potentially very fruitful from our perspective, experiment to be done. So it's very exciting. Now I come to cosmological aspects of this model. So I'm not going to go to what happened early universe. I don't know what is the early universe side of it. I'm going to talk about, in fact, more or less trying to bring it as close as possible to the Big Bang story. That is, I want to go just as much as I need to at least Big Bang nucleosynthesis takes place. Big Bang nucleosynthesis tells you that our universe must have been in some kind of an equilibrium, thermal equilibrium at around MeV at least, because everything works beautifully. From then on, we know everything is works. So we have evidence up to MeV scale that there was a Big Bang, at least up to that temperature. So what I'm going to assume that our universe at least was heated in some way, I don't know how, to some initial temperature, which is bigger than MeV. What temperature is, I don't want to assume yet what it is. Let's just say some temperature bigger than MeV. The bulk should have been empty by the time we get there. The reason is that if there was a thermal equilibrium between the bulk and the brain at that temperature, you would have the tower of all these sterile neutrinos all excited. And that would be inconsistent with N effective being around 3 in the observations in cosmology. So therefore, it better be that we started with essentially nothing in the bulk of the 5 dimensions, but basically we, like our universe, like a hot coal with some initial temperature. How we ended up there, I don't know. I'm not even getting to say where or how we ended up there. But this seems to be forced on us if we want to continue with this scenario. Okay, so let's start with some initial temperature and what's going to happen. Well, the interaction of the standard model fields couples to full gravity thanks to Einstein's principle of equivalence. There's energy momentum tensor on the 3+1 dimensional brain that we live on, and that couples to the metric in 5 dimensions, where you set the value of the metric variable to be at the place where the brain is, where let's say that's at z equal to 0. So we have 4 x's and 1 z. You just go to the position where the graviton is interacting with the energy momentum tensor. You can decompose the graviton in terms of its modes, in terms of this extra dimension. And these are what I mean by Kaluza-Klein modes of graviton. There's this expansion in the Fourier modes, or whatever the eigenvalue of Laplace in this extra space is. And roughly speaking, the mass of the nth mode will go basically like n times the Kaluza-Klein mass, because it's 1 dimension. And so like n over L. This is the tower of these massive gravitons. and they couple to energy momentum tensor. Now, imagine we have in thermal equilibrium. If you're in thermal equilibrium, the energy momentum tensor is not zero. It's expectation value, and it's coupling to these fields. It will drive creation of these graviton modes in the bulk. So you automatically create gravitons without, you don't have any control of it. Equivalence principle tells you will, and it will tell you at what rate, because the strength of the interaction is fixed by the Planck scale in 5 dimension. So everything is fixed. You just give me the temperature, it will tell you how much you will create of these extra gravitons. So we have now a prediction just from that initial temperature, what you create and how much. You cannot control that. You cannot say, I don't want to create them. You will have to, because that's Einstein's theory. So you have a situation like this. This is the tower of KK gravitons, separated by milli-electron volt to electron volt regime. And this is the place we are at, and this is like hot, some initial temperature. And what's going to happen is that they are going to create gravitons in the bulk at a temperature, at a wavelength or energy scale related to the initial temperature that you set it at. So mostly, depending on what the energy scale is, we know it's much more than the electron volt because it should be bigger than MeV, at least. At some initial temperature, you're going to start populating these gravitons excitations in the bulk. And once you have created them, what's going to happen? Well, they're going to decay because there's no reason they are stable. The gravitons are not, these excitations are excited states, and there's no reason they are stable. So it looks like a bad model in the sense that this cannot be in any sense related to dark matter because they're going to decay. Except they are gravitational. They're gravitons. They are weakly coupled, and the coupling strength has to do with the mass of them, and their mass is small, relatively speaking. Therefore, the decay rate is going to be slow. Very slow. So there you're going to create these guys at some initial temperature, let's say here 1 GeV, for now I will say why we're choosing that, and then they're going to start decaying down. It turns out that if you set the initial temperature to be GeV, around GeV, the matter graviton you have to produce will have exactly the right abundance to be dark matter. So the dark matter is the answer to the question I was asking. What is this tower of light particles not interacting are? Why haven't we seen them? The statement is we have seen them. That is the dark matter. And it's weakly interacting as predicted. So for the first time, from the principle, we are unifying the dark energy with dark matter. The weakness of dark energy predicts the existence of dark matter and the fact that it's weakly interacting, both at the same time. So they're all connected into one package. So we are unifying the full dark sector into one object. And more than that, they start decaying. They start decaying, but you can actually estimate the rate. Why can we estimate it? Well, these are gravitational, and the channels of interactions are available. You can just count it, and you find the decay rate, not a problem. So all of these can be done universally, and you find that they decay with the rate. The mass goes down, the average mass goes down. So it's basically reshuffling of the mass composition. You don't lose energy too much because the decay products are almost at threshold. So the mass goes down, but the total mass in dark matter doesn't change appreciably, but the average mass of the dark matter goes down at the rate t time to the power of minus 2/7, this power. And so they are created at the GeV scale, slightly above it, and by the time you get to our time scale, so this is the time axis, by the time you get to our time scale of 10 to the 18 second or so, you find that they are about 50 to 100 keV range, the masses. Now, when these matters decay, a graviton decays to a pair of gravitons, they get a kick velocity because some of the mass is converted to kinetic energy. But if you assume that, why this happens because of the inhomogeneities of this extra dimension, if you assume that the violation of the quantum numbers of this decay is of order delta, you find that the kick velocity that they receive is, if you do the calculation, you find this lambda to the 128, which is about 10 to the minus 4 times the speed of light. So they have the decay products, the dark matter, when they decay, they have a speed which is 10 kilometers per second or something like that. So there's actually an interesting feature that this dark matter actually is going to be a little bit, it's going to affect the structure formation somewhat. Namely, they are created where the structure is there, but they decay and they move away from where they were clumping the matter around them. So it will impact the structure formation. But interestingly enough, we checked whether or not this is going to mess up the structure formation, and precisely this is about the range which is perfectly okay with what's been observed. And so therefore, again, we are safe with that scale. But there is another thing that we have to worry about, that the dark matter, just the way it was created by the excitations in our brain. The graviton was created, but they can decay back to photons. So they can decay back to our universe, and they will impact, for example, CMB. So they will have some inhomogeneities in CMB on top of what we have seen. Would that mess that up? Again, the bound is such that it's okay, and it turns out if you look at the mass of the dark matter today, which is in this green range here, we are perfectly fine because the CMB bounds are above it, and so this gives you, again, just like the right region. It's crucial to note that the mass of the dark matter today, if it hadn't decayed, would be in trouble. If it stayed at the GeV mass scale, then it would have been violating the results. So the very fact that they are produced at the GeV scale, but then they become lighter as they decay, is necessary for it not to cause problems with CMB. And there are other things like extragalactic background light and so on and so forth. They're consistent with all of these experiments that rule out these regions. So this consistent with the mass, and this lambda parameter is the strength of the interaction, which is of order 1 for us, which is in the right range. So there are additional puzzles of cosmology, and this is what I want to say as the last topic, is why do we live now? By that I mean, why is that time now is related to the dark energy, which is 1 over root lambda? That was the 10 to the 60 I was showing you before. The 10 to the minus 120 square root is that 10 to the 16 fundamental units. Why do we live in that time scale? And another question is dark energy stable or not? Now, both of these questions are related to some things that we have thought about in the context of Swampland program. And so I will explain what will explain both of these facts, which is, before I do that, I want to say that this is related to yet another problem, which is what one could call the cosmological coincidence problem, is that why is the matter radiation temperature, that is the temperature in which the matter and radiation densities are equal, why is it so close to the temperature in which the dark energy takes over? So why should they almost be at the same range, like in our universe? In fact, this coincidence of these scales was what led Weinberg to predict that the dark energy is going to be this region. So let me remind you of the anthropic argument in this context. What he said was, if the dark energy was a typical value like order 1 in Planck units, it would be huge, and you would never have a time where the matter takes over the universe. It's always going to be inflating away, and you would never form any structure. So that would not be possible to have any structures like galaxies or us to exist. Therefore, we would not have even existed. So it should have been much lower than that for it to even existed. But at least, in other words, at least it should be below where the matter comes to be. So he would say, okay, so why is it not very, very low? Well, because that would be really fine-tuning. So he says, don't assume any fine-tuning except for our existence, which means, well, that means that this line should be basically as much as is allowed up to that range. So he predicted the range roughly in that range, and he got, surprisingly or not, the right answer, effectively up to a factor of 10 or 100. Sounded quite impressive. So that was the anthropic prediction for the dark energy. Here, actually, we would like to offer a different explanation of the anthropic principle. And that's related to this transplanckian censorship conjecture. So this is something we cannot prove in the context of the Swampland program, but let me tell you what this conjecture is saying and why we think it may be true. So take an expanding universe, whose metric is the usual minus dt squared, plus something which rescales the whole space. It could be exponential or something, it doesn't matter. The statement is that if you have a universe like this kind of universe, it should not be possible to make regions which are smaller than the Planck scale, which are believed to be unphysical in the theory, to become bigger than the size of the full universe, the Hubble scale. Because if you did that, they would freeze, and they become classical objects. In other words, this would be a machine, this expansion will become a machine to convert sub-Planckian quantum fluctuation, which are unphysical, to physically classical objects that you can see. Sounds bizarre. Okay, we cannot prove that this is true, but let's assume this can never happen. What this means is that the final value of A to the initial value, in other words, the expansion amount, cannot make length of the Planck scale be bigger than the horizon at the final stage. That's what this means. Sounds not too unreasonable, but we cannot prove it. What is the evidence for this? Well, it turns out that if you use this, it puts a bound on what potentials you can get. Because if the potentials are not steep enough, then you will have an expansion which lasts much longer, and you will violate that statement. So you find that if, for example, if you look at exponential potentials, you find that the exponent in the Planck units should be bigger than 2 over square root of d minus 2. And if you ask, suppose I want to have a regions of potential where the potential is flat, like inflation, like constant. You find that's not possible for a large range of field, as long as the longest you can have is delta of the range being given by this square root of d minus 2 times d minus 1 times log of the 1 over v. It turns out that both of these bounds have been observed in all the string constructions, and these directly follow from the trans-Planckian censorship conjecture as well. So we can derive these bounds, which is observed in examples in string theory, from this principle. So if you assume that, you can explain the why now problem. We live now because guess what? The universe cannot exist much longer because it would violate the trans-Planckian censorship conjecture. So in fact, if you have an exponentially expanding universe and you want that to be less than 1 over h, it will tell you that the maximum lifetime of such a universe is 1 over h up to a log factors. That means the typical scale in that universe is of order 1 over h. So we are just sampling a typical lifetime, a time scale in that universe. So that will explain why now problem. And this will also tell you that the dark energy cannot be stable and should evolve in Hubble time. Could that be related to the recent experiments that at least these are preliminary results by Desi, which suggest maybe that's what's happening? It's too early perhaps to say, but that's an amusing possible connection with experiments. And finally, I want to connect it to the initial temperature I chose. I told you that the initial temperature on the brain should have been about 1 GeV to give you the right amount of dark matter. I now want to actually explain why 1 GeV is the natural one to choose. So I want to give you a principle of why that should be 1 GeV. The reason would be we want to have a 4-dimensional Big Bang scenario, which means that these higher dimensional moduli, higher dimensional fields, which control the sizes of these extra dimensions, should have frozen by that time. That means they should have had some mass which have frozen them. How much mass they should have had? Well, whatever mass they should have had, presumably at some point they were excited. But they should decay away by the time we get to this. Otherwise, you will have these vibrating universes, and we don't want that. What is the rate of their decay? The rate of the decay they should be proportional to 1 over m Planck, the amplitude, because they're gravitational coupled. So that means their rate should go like the mass cube divided by m Planck squared, and they should have decayed before you get to the Hubble time, which gives you the rate should be bigger than the Hubble rate, lambda to the 1/2, which gives you that the mass of these fields is bigger than lambda to the 1/6, which means that their mass is bigger than GeV. So therefore, the initial temperature, if the initial temperature is bigger than their mass, they will excite them. So it's safe to be less than this bound for them not to be excited. So the natural range of parameters would naturally land you at lambda to the 1/6. And lambda to the 1/6 is precisely the one which gives you the right amount of dark matter, and it makes the matter radiation temperature be the same temperature as the dark energy temperature taking over. Explains the coincidence problem. So the coincidence problem is no coincidence if you take this into account, in the context of the trans-Planckian censorship conjecture. So all these coincidences are coming back to simple ideas from quantum gravity, and there could be easily falsified, maybe too easily, perhaps for my comfort, which is the following. The Newton's force law, 1 over r squared, should become 1 over r cubed if you are much less than 1 micron, and that's easily checkable. Well, easily maybe it's not too easily, but very close to it, because you would predict that the first order correction to this will be some kind of a mass exchange for these gravitons, which give you a correction of this order, of this form. And the next round of experiments, which are actually happening right now in Vienna, for example, by Aspelmeyer's group, are actually looking at this range, and they think they can get to about 10 micron within 3 years or so. So these are definitely within the range of things people are going to be seeing soon. In fact, this is their experiments that they are doing with some kind of a attractor with the torsional pendulum, which oscillates as you rotate this attractor pendulum, object here. And the experiment is being done in a mine shaft about an hour away from the Vienna to keep the vibrations and all that under control, which is one of the major challenges. And there are many other challenges, so it's by no means a trivial experiment, but it's ongoing. So let me summarize. Sorry, running over time. So the smallness of the dark energy and the swampland plus observation leads to the prediction of the dark dimension in the micron range, unifies the dark sector. Dark matter could be nothing but the tower of gravitons. It unifies gravity with the dark energy, with the dark matter, because after all, you don't need to postulate a new particle for the dark matter. It's just graviton. No direct detection of dark matter is possible because they're gravitational. So all these, we are predicting that all the direct detection experiments, unfortunately, will fail to detect the dark matter. Axion mass is similar to the neutrino, it's similar to the other tower scales. And now you can see all these powers of lambda to the 1/12 are fixed by this theory. The 1/12 power was the Planck scale in the higher dimension, is the decay constant of the axion, is the instability scale for the Higgs. Lambda to the 2/12 is the weak scale or QCD scale, is the initial temperature for the cosmology. Lambda to the 3/12 is the neutrino or axion or the dark tower scale. And lambda to 6/12 is the Hubble scale. Thank you.
Thanks, Cumrun, for the beautiful talk. Cumrun will be around here tomorrow, also next week, so if you want to discuss him, but now we will take maybe a few questions, please.
The Higgs instability scale is rather sensitive to the top quark mass, and so it seems like it must just be a coincidence, this what you're finding, because it's hard to believe that just changing the top quark mass a bit would put the UV extension of the standard model into the swampland.
Perhaps, but I think that the way you're raising the question is precisely the way an effective field theorist would raise it, which is precisely what's not true. So let me explain. So that mindset, that I can just change this parameter without worrying about this, how could this thing do that, which is the correct mindset for effective field theory, is precisely what I'm saying is at this center of the problems for why effective field theory can miss these points. Namely, the UV and IR are delicately related. It is not like, oh, I can just change this parameter. This cannot be related. No. You cannot do that. In other words, you would have been able to do that if you just said, I can couple every field theory to gravity. That cannot be done. The parameters are amazingly, looks like it's amazingly fine-tuned from the effective field theory viewpoint. And that's the nature of the swampland program. So that's precisely why the solutions to hierarchy or these fine-tuning problems is not going to be found within the effective field theory approach. It's going to be found from the quantum gravity approach, we believe. So then that's one version of the answer to your question.
Fernando?
Very nice talk, Cumrun.
Thank
you. I have like many questions, but let me ask you two of them. One is that at the beginning you said that, but the thing that I like about the swampland is that you're looking for very general predictions of quantum gravity, which is good. So in that sense, you have you used that to rule out other approaches of quantum gravity? For instance, that's question one. And so question two is,
Sorry, you're asking if we can rule out all the other approaches of quantum gravity?
Or any of them? Have you applied that to any?
So let me say what we can rule out. If an approach in quantum gravity allows you to have global symmetries, we can rule it out.
No, but I'm saying concrete proposals, like, loop quantum gravity or causal set approach.
I would say that the aim of this is to rule out the predictions, some of the predictions. We are not trying to rule out an approach.
Okay.
So this, as I said, we are open to other possible quantum gravities without biasing ourselves. We don't want, as I emphasize, we don't want to bias ourselves that string theory is only the game in town. We want to see if we can derive it, and if it's not, we learn about whatever it is. So that's my view is we should not bias ourselves. And to the extent that we have already a bias because we are getting our construction that way, we should always be skeptical about things that this is driving us. So we are being open. But what I find surprising is that a lot of these principles reinforce what we have found. So occasionally we think, the string theory is giving a very small corner. You should have more possibilities. Why are we not getting it using string? And then we find later the reason was an anomaly we had missed or some other thing and so forth. So it seems like always reinforcing. But yes, absolutely we are open to other possible approaches.
Okay. And then the other point is that since the original idea is to be very generic, what will you rule out if this is you will not rule out the string theory, you will rule out your scenario? What is it that will be ruled out if you don't find
Yes, good question. We are physicists. We should always be open to our theory being ruled out by experiments. After all, it's an experimental science. So what if they do it, Fernando's asking, what if they did this 1 over r squared experiment up to 1 micron, they don't find it, any deviation for Newton, and if, let's say they go to 0.1 micron or even 0.01 micron, and they still don't find it, okay, what happens here? So what I would say I will learn there, or the first option that I would be driven is that, did I get the exponent? So you remember I said that the mass tower should be lambda to some power. And that power is between 1/2 and 1/d or 1/4. Could I have gotten that bound wrong? Could that 1/4 be 1/5 or 1/6 or what? So that would be the first thing I would worry about, that the argument for that, could that be false? The next thing, if you go further down and you won't find anything, then the next thing would be, is there something wrong with the distance conjecture or duality conjecture in the context of positive energy? Could that be a counterexample for some reason? So whatever they find, we learn something. Based on what we know today now, this is the natural answer. But of course, we are humble. We learn from experiments, absolutely.
Maybe the last quick question, because we're a bit over time. Otherwise, we can continue after the talk. Sorry?
He had a question.
Sure.
No, he.
John?
I was just curious that what would be the first signal? Because you were emphasizing the deviation of gravity, but I imagine that also the dark matter decay, so there's injection of photons and so on, which can be measurable.
Yes.
Yeah, and then there will be future experiment. Is that going to be the first signal that
We
you
tried,
expect?
so we worked on we studied the astrophysical aspects of it with Cora Dvorkin and George Zobi to try to exactly ask this question. And it was not clear whether or not we would be in a range where they would be able to detect it. So it was very close to that. You kind of saw, I think I will bring it if you want. It is very close to the range of being ruled out, actually, but so for example, Tracy Slatier and company have actually studied precisely what are the decaying dark matter scenarios and how they would impact the CMB and so forth. So precisely for those ranges, you find what the bound is. So the ultimate bound that CMB will have is this dashed line. You cannot improve that based on no experiment. So the CMB right now is this pink region, but you can never get any better than this dashed region. And as you can see, you cannot get the region that we have based on that. So you don't necessarily will be able to rule this out or see it either way by CMB. There's a chance you might be able to see it if you go a little bit. Who knows? So there's a sliver of chance you might see it, but if you don't see it, that's not going to be ruling it out because we still have a good enough parameter range.
Okay, then. Spenta, sorry, I haven't seen.
Is there some way in which we will be able to experimentally observe the graviton or evidence for the quantization of gravity? Is it?
Well, it's a good question. I don't think it's directly related to what I'm saying, of course, but the effect of graviton and the tower we will be able to see that, and that's precisely the 1 over r squared going to 1 over r cubed. So that much we should be able to see if this scenario is correct. But I don't think I have anything more exciting to tell you from this scenario for measuring or seeing quantum aspects of gravity, unfortunately.
Okay. Please, maybe last question.
Sorry, just a quick one. You mentioned the length scale where you thought this could be falsifiable, but these measurements of gravity modifications also include a strength. So what strength would need to be ruled out at that length scale for you to consider this
You're talking about that alpha I was talking?
Exactly.
Alpha is order 1.
Okay.
It's just a number of gravitons, kk gravitons at that scale. So you have 1 or 2. So it's order 1. So some experiments are probing the region where alpha is like 10 to the 3. That would not be good enough. You should get to alpha of the order 1.
Great, thanks.
Okay. If there are no more questions, I suggest then we thank Cumrun again and continue after the talk.